Effective interdomain traffic engineering has three goals. One is predictability. In other words, it should be possible to predict how traffic flows will change in response to changes in the network configuration. Another goal is to limit the influence of neighboring domains. In particular, we'd like to use BGP policies and changes to those policies that limit how neighboring ASs might change their behavior in response to changes to the BGP configuration that we make in our own network. And finally, we'd like to reduce the overhead of routing changes by achieving our traffic engineering goals with changes to as few IP prefixes as possible. To understand the factors that can confound predictability, let's look at how the interdomain routing choices of a particular autonomous system can wreak havoc on predictability. Let's suppose that a downstream neighbor is trying to reach the autonomous system at the top of this figure. The AS here might wish to relieve congestion on a particular peering link. To do so, this AS might now send traffic to that destination out a different set of autonomous systems. But once this AS makes that change, note that it's choosing a longer AS path, now taking a path of 3 hops rather than 2. In response, the downstream neighbor might decide not to send its traffic for that destination through this autonomous system at all, thus affecting the traffic matrix that this AS sees. So all the work that went in to optimizing traffic load balance for this AS is for naught, because the change that it made effectively changed the offered traffic loads and hence the traffic matrix. One way to avoid this type of problem and achieve predictable traffic flow changes is to avoid making changes like this that are globally visible. In particular, note that this change caused a change in the AS path length of the advertisement to this particular destination from 2 to 3. Thus, other neighbors, such as the downstream neighbor here, might decide to use an alternate path as a result of that globally visible routing change. By avoiding these types of globally visible changes, we can achieve predictability. Another way to achieve effective interdomain traffic engineering is to limit the influence of neighbors. For example, an autonomous system might try to make a path look longer with AS path prepending. If we consider treating paths that have almost the same AS path length as a common group, we can achieve additional flexibility. Additionally, if we enforce a constraint that our neighbors should advertise consistent BGP route advertisements over multiple peering links, should multiple peering links exist, that gives us additional flexibility to send traffic over different egress points to the same autonomous system. Enforcing consistent advertisements turns out to be difficult in practice, but it is doable. To reduce the overhead of routing changes, we can group related prefixes. Rather than exploring all combinations of prefixes to move a particular volume of traffic, we can identify routing choices that group routes that have the same AS paths, and we can move groups of prefixes according to these groups of prefixes that share an AS path. This allows us to move groups of prefixes by making tweaks to local preference on regular expressions on AS path. We can also focus on the small fraction of prefixes that carry the majority of traffic. 10% of origin ASs are responsible for about 82% of outbound traffic. Therefore, we can achieve significant gains in rebalancing traffic in the network by focusing on the heavy hitters. In summary, to achieve predictability, we effect changes that are not globally visible. To limit the influence of neighbors, we enforce consistent advertisements and limit the influence of AS path length. And to reduce the overhead of routing changes, we group prefixes according to those that have common AS paths and move traffic in terms of groups of prefixes.